Hello, Honors Pre-Calculus. Today's notes are about 6-4, day 2, and we will be learning how to do things with orthogonal vectors, and we will learn about projection of vectors. So we're going to start with orthogonal vectors. And the vectors u and v are orthogonal if u multiplied by v, not multiplied, sorry, u dot product v equals 0. The terms orthogonal and perpendicular, they're basically the same thing. We're meeting at right angles. And then this goes on to talk about the 0 vector, meaning we can use the 0 vector in this formula as well. All right, are the vectors u, which has a component form of 2, 3, and v, which has a component form at 6, 4, orthogonal. So we will do the dot product. You know what? I want to turn up my thickness. There we go. So the dot product is just going to take 2 times 6 plus -3 times 4. And that's going to be 12 minus 12, which equals 0. And the formula says if it equals 0, then they are orthogonal. And then over here, I have a picture so you can see the 90-degree angle in there. Okay, finding vector components. So we've already seen applications in which 2 vectors are added to produce a resultant vector. Many applications in physics and engineering pose the reverse problem, needing to decompose a given vector into the sum of 2 vector components. So in this picture below, there's a boat on an inclined ramp, and the force is going to be called F, due to gravity, pulls the boat down the ramp and against the ramp. These orthogonal forces, which we'll call vector W sub 1 and W sub 2, are vector components of force. So the force is equal to W sub 1 plus W sub 2. The negative component, W sub 1, represents the force needed to keep the boat from rolling down the ramp, whereas W2 represents the force that the tires must withstand against the ramp. The procedure for finding W1, W2 is shown on the following page. But then here's a picture of talking about force, and then we've got the gravity pulling the boat towards the water down the ramp, and then we've also got the gravity pulling it just down in general, and where the tires are pressing against the ramp right there. Okay, definition of vector components. So we're going to let u and v be non-zero vectors such that u is equal to vector W sub 1 plus vector W sub 2. And W sub 1 and W sub 2 are orthogonal. And W sub 1 is parallel, or it's parallel to or a scalar multiple of vector V, which we'll see in figure 6.37 below. And then the vectors W1, W2 are called vector components of U. The vector W1 is the projection of U onto V and is denoted by W sub 1 equals projection sub V onto U. Or I should say of U. Projection onto V of U. The vector W sub 2 is given by U minus W sub 1. And so here's those figures that they were talking about below. So you can see the u vector, and we can see the v vector. And then the W1 is a scalar vector of v. That's what I was saying above. Or W2 could be the scalar vector. Which one does it say up here? Yeah, W1 is parallel to or the scalar multiple of v. Okay, and then the same thing on this one here, only the v is this way, but our angle is obtuse, so the W1 would project the other direction. You can see if we drop down from the end of the u vector, it's going to make 90 degrees. And there's that orthogonal. So from the definition of vector components, you can see it's easy to find the component W2 once you've found the projection of u onto v. To find the projection, you can use the dot product as follows. So we're going to do u is equal to W1 plus W2, which is also equal to a scalar of v plus W2. And then, excuse me, on the next step, what we're doing is we're doing the dot product of v to both sides of the equation. So as long as we do it to both sides, we can do whatever we want. So we're going to do the dot product of v to both sides of the equation. So on the right side, that's kind of like distributive property. We have that in our properties from, I think it was the beginning of 6.4. And from that, excuse me, we can determine that the C times the vector times itself, which is the same as the magnitude squared. That was another property that we had. And then over here, these two things should be 0 because the dot product of W2 and V are orthogonal. So here's a formula that we come up with from this. And then W1 is the projection onto V from U, which is equal to CV, which is equal to U times V over the magnitude squared of V multiplied by V. So this is the formula that we will use for projection of U onto V. So here's an example. I'm going to decompose a vector into components. We're going to start with the W1. W1 is equal to the projection let me just put that using their symbols on the previous page. Projection of U onto the V. And that's going to give us the formula of U dot product V over the magnitude of V squared, and then we multiply that by V. So let's see on top. We're going to do, 18 plus negative 10 over, we're going to do the magnitude of V. So, well, and then we're going to square it after that, so don't really need that. Be 6 squared plus 4 is 40. Oops, and then I have that times v. Vector v is 6, 2. So I'm going to get 8/40 multiplied by 6, 2. So go ahead and multiply that out, and I get the vector 6/5. Well, yeah, because this reduces. Sorry, I meant to say that earlier. 1/5. 6/5 and then 2/5. Okay, and now to find W2, we're going to do vector u minus W1. And this was W1. Okay, so I'm going to have vector u, which is 3, -5, and we're going to subtract 6/5 and 2/5. That'll give me, let me change my denominators here. That'll be 15/5 and -25/5. So vector W2, what are we going to get? 9/5. And then -23/5. Nope, I forgot to subtract. 27. Okay. So u, oops. U is W1 plus W2. And we've got our W1, which is 6/5, 2/5, plus our W2, which is 9/5, -27/5. And let's see, it's going to give us 15/5, and that'll give us -25/5, which equals such a nice number. Let's see, we get 3. My computer just told me I have to plug it in, so I got distracted. -5. Grab my cord, get my computer plugged in. Hopefully nothing dies. Okay, I am back. All right, so our goal was to find we were just going to write u as a sum of the two orthogonal vectors. So that's what we did. We wrote u as the sum of the two orthogonal vectors, and we got the vector of 3, -5 for u. Now that's all the notes for today. If you have any questions, feel free to get a hold of me, ask, send emails, make sure you understand how to do these. And then your assignment is in the book. Have a great day.